The next speaker is from Jasper. It's Sai Karthik Madabhushi. Sai is Jasper's senior field application engineer based in Watford in the UK. He specialises in formal verification methodology and applications from Jasper to solve verification needs of Jasper customers. He has extensive experience in product development of formal verification tools and verification IP. And his talk today is entitled Formal-Based Coverage-Driven Verification. So I'll hand over to Sai.
Thanks, Mike. Good morning, everyone. The theme for my presentation here today is coverage metrics in formal verification. Today, as the presentation goes, we'll try to understand what these metrics are, how do they impact you if you're a regular formal verification engineer, and why are they so important. Before I dive deep into the details for this, let's just take a step back and look at where formal verification has come in the last few years. Back in 2004, when I started writing properties and verifying RTL, most customers were just using traditional formal verification. And then somewhere along the road came connectivity and post-silicon debug. And it's 2014 now, and you have a host of applications to verify different verification challenges in your day-to-day affairs, like register verification like you just saw before, or probably security path verification, verifying secure regions in your SOC, low-power modeling for formal verification using the low-power app. So there are a host of applications where formal is contributing to verification as of today. And our CEO, Catherine Frenin, predicts that in the days to come, formal will dominate verification. So if formal will dominate verification, how is this important for us? We need a credible metric to measure the amount of formal verification you have done so far so that you can sign off on your formal verification effort you have done. So when I say coverage, what are the things that spring to your mind? Well, is my property set complete? Are my constraints allowing all valid stimulus? Or am I done with my formal verification? But then I already have simulation coverage metrics. Can formal augment or help me in attaining closure when it comes to simulation? So so Jasper's coverage-driven strategy is basically two-pronged. The first one, most of you are familiar with. It's the simulation coverage closure flow, where you can take your simulation coverage database, read it in, and identify all the unreachables and help you in closure when it comes to simulation coverage metrics. So the second one is actually coverage metrics for formal verification. The idea is to define a metric, and Jasper has come up with one to quantify and qualify the formal verification effort you have done so far. And this will be the focus of my presentation here today. So formal specific coverage metrics or coverage metrics for formal verification. What does it mean? So firstly, most people would be interested in knowing, are my constraints allowing all legal stimuli coverage? Well, have I written enough assertions? Property completeness. And how much formal verification have I done so far? So you can use proof coverage or bounded proof coverage to assess the amount of formal verification you have done on your RTL so far. And these metrics will be the focus of my presentation today. Jumping into the first one, stimuli coverage. So in the first case, your designer runs your RTL in a completely unconstrained way. And whatever portions of your RTL haven't been hit are dead code. So the designer or the verification engineer can actually analyze the RTL and figure out if these portions are intended, or maybe it's just a default case statement you have put in there because your linting tool is just complaining, or your company's design coding standards, you've just put in a few statements. These will probably never be hit, but then you have to put them anyway. So if they're valid, then the designer can waive them. And if they're a problem, if they should have been covered, and if they're not covered, then the designer can fix them. So this will form your baseline. So this will be the base snapshot, which you will be comparing your formal verification results ahead. Once you get the baseline, you can add in all your constraints and verify your RTL. Now when you add your constraints are typically used to either prevent illegal scenarios or direct your formal verification in a certain way. So once you add your constraint, a certain set of a certain portion of your RTL will be hit or will not be hit. As a result, so you have the baseline. Now you have a baseline to compare this result with once you add your constraints. If the unreachables in your second run are intended, are expected because of the constraints or any other design artifact, then your designer can just waive them. But if they are contributing to an over-constraining scenario, then the designer or the verification engineer can fix your constrained formal test bench or your constrained environment. And this is the basis or concept of stimuli coverage. Now going to the next one, and probably more interesting one when it comes to formal verification engineers, property completeness. So let us say this gray box here is your design, and it has all the cover points or design elements there, and you have written 5 properties, P0 to P4, to verify this piece of RTL. So how do you know these 5 assertions, properties, are enough for your formal verification? This is what a designer or verification engineer looks at. But then this is what engine looks at. So the engine structurally traverses right from the beginning of the assertion all the way to the primary inputs or any undriven signals, and it forms a virtual cone. And this virtual cone impacts this assertion directly. This cone is called the cone of influence for a given assertion or property. Now, you have a set of colored region there, and you have a gray portion. Let's say the colored region, let's give it a number. Let's say it's 50. And so 50% of your RTL is being covered or being verified by these 5 assertions, and there is 50% more which is not being verified by any assertion. Well, and this is the concept of property completeness. Is this good enough? Because the engine is structurally traversing through the RTL to figure this out. And no, because what the engine structurally traverses, it condenses it, or it compacts logic to a much smaller portion. And the engine uses a lot of optimizations like constant propagation, honoring constraints, cut points, and a lot of other non-deterministic optimizations to actually slice a portion of the fanning cone here, a portion of fanning cone there, and you end up with a picture like this. Eventually, when the problem is presented to the engine, and this is the picture the engine sees. Now the cones are not whole anymore, as you can see. Let's say the color shaded portion or the colored portion is 38. So only 38% of your RTL is actually being verified using these 5 assertions. 62% of your RTL does not have any assertion covering it. And this is the concept of property completeness that Jasper has come. The shaded portion there is actually called the proof core. It is the actual core which is verified by the engine while proving that property. And this metric is called proof core metric, which is used to define property completeness. Well, can you tell anything more from this proof core metric? So let's take a look at assertion P0 there. Let's say you have a bug somewhere around where you see the arrow. Any RTL present in that particular cone impacts or is affected by the property there, or should I say, the property affects any piece of RTL in that particular cone. Let's say you have a bug there. The tool will find you a counterexample for that particular bug. So what does this tell you? Observability. Or any point or any portion of RTL in that cone is observable by 1 or more assertions in your design. So proof core metrics can be used to answer the questions of property completeness and observability of different portions of your RTL vis-a-vis the assertions you have specified. This is all good if you get full proofs, but then most experienced formal verification engineers know that it's not always easy to get full proofs in your design because of design complexity or, let's say, verification complexity. You sometimes don't achieve full proofs. What do you do then? Well, you can just be upset, or you can hit the panic button, or you could use bounded proof coverage to estimate the amount of RTL you have verified using bounded proofs. So what are bounded proofs? Bounded proofs are assertions which have not converged convincingly. So people generally see proved or a counterexample when it comes to a given assertion. But when the two cannot converge convincingly, you get something called a bounded proof. And it comes, and you see an interesting number along with the bounded proof, and that is typically the bounded depth of the bounded proof in an average design. So can you get value, as of today, can you get value of bounded proofs? So most people, most experienced formal verification engineers, do something like this. They calculate the flop boundaries from the input to the output, or they factor in counter sizes or FIFO depths or the different FSM states in your design, and they estimate a number n or a period window where they anticipate the maximum number of counterexamples. And they say, let's say I have run this design till a depth of n or n plus 2. And if I haven't found the counterexample till that, it might run for a day, it might run for a 2, but then if the tool reaches this depth is good enough for me to sign off on my formal verification effort. Quite a lot of experienced formal verification engineers do that today. But where's the pitfall in that? Let's say you made a mistake in calculating that number n, and at n plus 5 somewhere, due to some modal behavior or due to some latencies you have not taken into account. There's a bug existing somewhere there. How do you factor that? So Jasper's unique bounded proof coverage metric, what it does is it analyzes your RTL and it takes all these into factor, and it gives you the deepest cover point or the deepest point in your RTL which impacts that assertion. So it will come back to you with a number, let's say 30 or 35, and say, okay, there is a cover here, or a cover point in your RTL, which is being hit at a depth of 35, and let's say you've just run it till 20 or 24. So it says, okay, we've found a couple of cover points which are being hit at, let's say, 28 or 32, and you've just run it till 24. So these are in the proof core or the founding cone of the property, and you need to run it to a depth of at least 32 or 34, whichever is the suggested depth by the tool, to get more confidence in your boundary proof. Is this, well, if you run it to the depth of 32 or 34, does it mean that there's no more counterexamples? No. It means that the tool has gone through or visited all states till a depth of 34, and it has not found any counterexamples. And, well, that's starter. Secondly, you can extract all the RTL cover points, everything that have been hit till a depth of 34, and add it to your Proof+COV metric, which you have generated earlier. And this will give you a much better picture of the verification you have done. So from a verification flow perspective, from a verification project perspective, let's just consider the graph here. On the y-axis, you have bugs found during the verification cycle, and on the x-axis, you typically have the verification progress by the verification engineer. Initially, you write a bunch of assertions and try to verify your RTL. You find a lot of counterexamples, a few converged results, proved results, and then you run the Jasper coverage app. Property completeness, you get to know if you're missing any assertions, then you write your assertions. Using stimuli coverage, you can figure out if you have over-constraint your environment, you can fix your environment, adding more assertions, fixing your environment, and then this will be followed by a second wave. A much smaller wave though, but these bugs which have been found in the second phase are deep bugs and are equally important compared to the bugs which are found in the first wave. So this is how Coverage app can help you improve the quality of your verification and increase confidence in the formal verification you have done so far. This is not just something theoretical. We have had a select set of customers who have used it. APM on the West Coast in the US, they had used the Coverage app for closure. Here was a very experienced formal verification engineer. He had his test plan, he wrote it exhaustively, and he wrote his assertions, and he verified his design. Well, he was doing CPU blocks, so, well, getting converged results were a big problem. So he had some converged results, and in the first phase, he got about, when he used the coverage app, he got about 19% coverage. And he was really surprised, saying, okay, why is this happening? And then we suggested he add the bounded proof coverage and add it to the Proof+COV metric. And when he did that, his coverage improved to 99%. So bounded proofs, he spent about 2 days running them to the suggested depth of 25 or whatever. And he's got, he has exhaustively verified his design. Now, how can he take credit for it? So bounded proof or bounded proof coverage metric is a very useful way of getting credit for the verification you have done so far. Here is a brief summary. So, summary of my presentation here today. So, using the coverage metrics, which have been designed for formal by Jasper, you can try to address the problem of property completeness, and you can also get a visibility into the observability of your RTL vis-a-vis the assertions. You can use stimuli coverage to identify any potential over-constraining situations in your design, and You can also use the coverage app to help you in simulation, coverage, closure flow. And that's it. I'm done.
Thank you, Simon. Is there any questions? Mike?
Mike Benjamin, I'm a consultant. It seems to me that your definition of property completeness is a bit like line coverage. It's a lower band. It tells you if it's a bit of your design you hadn't touched at all. It doesn't really tell you if you've tested all the functionality. So it's not clear to me what value it adds, as most of the formal we write we don't expect to be totally exhaustive and could be checked by functional coverage points. So what heuristic proof is there? I mean, you gave some indication that some of your customers have tried this, but how are you trying to validate that it actually adds value in the same way? But, for example, we still use line coverage even though we know it only tells us a very limited thing about our verification.
That's a very good question. So the thing here is that your metrics are only as good as the coverage data points you're using. If you're going to just use line coverage, then that is what it's going to show. If you're going to use branch coverage or expression coverage, you can all add them and improve improve is not the right word, and you can add all these metrics and they can be run in the coverage app to get you a much, better idea of the quality of verification done. So if you're just going to use line coverage, then that is what you're going to get. So if you're going to add branch coverage, toggle coverage, or expression coverage there, then that will give you a much better metric to qualify the verification you have done so far.
I guess my point was I think your formal coverage metric is a very weak one, and I'm not sure it's adding much value. So that was my question, and what evidence is there that it actually adds value?
Tim Blackmore and Finian. So I just follow on from that. So very specifically, if there was, if you inserted a fault in this proof call, would you get a fail on property?
If you have an assertion there, and the assertion is, if you have an assertion and in the proof code, if there is a fault there, it should be able to catch the counter, and you should be able to get a counterexample.
Okay, but can you say yes? I mean, is it
Yes.
guaranteed?
Yes.
It's guaranteed.
I have one question as well. I always wonder how these formal metrics tell us which simulations we don't need to do anymore. Is there any way of using these coverage metrics to say, well, you can now stop doing this type of simulation because now I know I've done this formal proof. I can cut out a certain amount of simulation. Because at the moment, formal is quite often an add-on. And if you go to your manager, what you really want to be able to say is, I can save simulation by doing this formal, and here's the proof of these coverage metrics. So do these coverage metrics help me go to a manager and say, we can stop doing this type of simulation?
Sure. Till date, you didn't have a measurement or a metric to actually to quantify the amount of formal verification you have done so far. So using the coverage app, now you have a metric to say, this is the amount of formal verification I have done. And you can use that metric to sign off on your formal verification effort. And so if you formally verified this block, you don't need to run simulation on it.
Okay, but that's presuming if you've done a complete verification.
No, because a bounded proof is far more valuable than hundreds of simulations you have done. So using the coverage metric that you have extracted from the bounded proof, you can actually sign off on the effort you have done.
One question about this computation to generate the bound. Actually proving a theorem, proving assertion is correct or not correct is as complex as finding the design radius of the finite state machine for that design. So it's actually the same complexity. And I don't see how you can, if you are not if the tool is not, let's say, if you cannot decide the property, how you can generate the bound. It's the same complexity.
I'm sorry, I didn't get your question.
I think what it's saying is it's the same complexity of algorithm to find the bound as it is to do the proofs. Is that correct?
Fair enough. That's a good question. And the idea is not to find the bound beyond which you will not find a counterexample. The bound that we give for a bounded proof is typically the depth of the deepest cover that will impact that particular assertion. And in and around that, maybe, let's say, a depth of 30. And let's say at 30, that is the deepest cover item that was hit by the property. But the engine probably needs to do a little more to actually get a full proof for that. And the idea of a bounded proof is not to tell you for sure that this is the depth at which you will get a full proof. And if that was possible, we would have given a full proof anyway. So the fact that you have a bounded proof means that it is a depth till which, if you run the engine to this particular depth, then you would have hit all RTL cover points which impacts this particular property. And you get a much better confidence in the bounded proof or the depth you have run it to.
Okay. I think there are no more questions, so thank you very much, Desai. Thank you.
Thank you, Mark.